Yay. Thank you. Thank you for the encouragement. I love you all. Where did Luke go? Why did Luke just leave? What's he doing? Oh, okay, got it. No, that's totally, yeah, thank you. I was totally fair. That's totally fair. No, I could just start. I mean, Luke already knows all this anyway. Okay. So, hi. I'm going to be presenting now about game theory and distributed computing. These problems that I'm going to be talking about are pretty much every distributed computing project is going to encounter some form of these problems. In fact, almost all of them very much explicitly have these issues, and that's what I'm going to be discussing. So, okay, there we go. So, distributed computing there aren't really any robust distributed computing anti-cheating mechanisms in use right now, right? So there are people are researching them, but the space is really sorely lacking, kind of proper incentives in this space. And while pricing mechanisms are a bit more prevalent, without anti-cheating mechanisms, they're not secure, right? So like you have, if somebody's giving you a price, if you don't know that the computer that they're providing you is accurate or legitimate, then the price could is just a suspect. And so we have to ask, what role do anti-cheating mechanisms and pricing models play in the larger scheme of distributed computing in general, right? Because anti-cheating mechanisms and pricing models are only kind of a subset of the problems faced in this space. Click here, there we go. So when a client receives, here's the problem, just the kind of really basic problem statement. When a client receives a result from a compute node, so what assurances can be made that the result of that computation is actually correct? So how do you know that the node is computing honestly? And let's set aside the possibility of faulty nodes for now and just say, how do you know that compute node isn't just giving you a result without actually doing the computation in order to get the price or the reward for computing it? And the second question is, how do we actually price that compute? Can we do it per job? Like if we could think about it like a Docker container or a WASM image, or per time? How do you actually price these computations? So there are a number of ways for avoiding cheating in distributed computing. So one approach, naturally, you can have snarks or fully homomorphic encryption, trusted execution environments, and verification via replication. And we're going to focus on verification via replication in this talk, and the reason being that for the cryptographic methods, snarks and fully homomorphic encryption and so on, they have very, very high overhead. And they will for a long time, and even kind of in the best case scenario, if you're talking about like having a computation, if you're using like Planck or something, you have to have a computation trace, and then you have to run some kind of at least linear time algorithm over that computation trace. There's always going to be a substantial overhead for snarks, unless there's some like incredible breakthroughs. We'll see, who knows. And then T's trusted execution environments they're known to have vulnerabilities. This may change over time, especially as the low-hanging fruit are kind of picked off. And we might come to a time when T's are very, very much trusted. But that's not the scenario right now. Another kind of a couple of things to keep in mind are the context of just global consensus versus local consensus. So there's a difference between, if you have a two-sided marketplace, there's a difference between the client being sure or relatively sure that their task was computed correctly, and maybe the compute node would also want to know in case the result is disputed. But there's a difference between like the client plus maybe a few other nodes knowing and being secure that the result was computed correctly, and then every node on the network being sure that the result was computed correctly, right? And so this is kind of local versus global consensus. Like in the kind of like natural explanation, like the natural example of global consensus would be something like a blockchain, right? Smart contract computations in a blockchain, for example. And so I'm just going to assume in this talk, non-malicious nodes, but nodes that are utility maximizing agents, right? So they're not going to specifically go out and try to mess up a result on purpose. The only reason they would ever do it is because they can make more money by doing it, basically. Yes. So the kind of like basic idea behind verification via replication is to verify occasionally. Now you can, for example, just do 2 or 3 copies of every job, but this is kind of relatively expensive. And once you start doing that, you start approaching the same costs that you would get with centralized cloud providers. And so that while there are still benefits to using the a distributed system, there are also benefits to using a centralized system in that case, and it becomes a bit less clear. So ideally, you want to minimize your costs. And so we need to, there's a few problems. So we need to, if you're doing verification via replication, you need to know that the nodes that are verifying each other don't collude on the result, either correct or incorrect, right? So they could collude on an incorrect result, so neither of them compute it, and then they just send you the result. And now you're kind of in a really bad spot because you just both nodes gave you the same result and that result is wrong. Alternatively, the compute node can one of the compute nodes can compute the result honestly and just send that result to the other node. And while that's not the worst scenario, you want to generally kind of avoid that. So there's a whole space of solutions in here. I'm just going to focus on 2. One of them is based on the paper. I'm just going to skip to the end right here. By Dong et al. Betrayal, Distrust, and Rationality, Smart Counter Collision Contracts for Verifiable Cloud Computing. And the method they use there is basically they take 2 nodes and the 2 nodes that are supposed to be verifying a job, and they put them into something they call a prisoner's contract, which basically puts the 2 nodes into a kind of they design a game, which is basically the prisoner's dilemma game, where the 2 nodes have an incentive to give each other false results because they'll get a higher reward if they're correct and the other node is wrong. And the way you do that, of course, is we're going to have, this is in the context of having deposits and collateral, as this is kind of a standard assumption in these scenarios. And so. And then, of course, hypothetically, those 2 nodes could collude on could collude to say, actually, we're going to override the prisoner's contract with our own contract, and then you override that with the trader's contract, which basically says, the first node to report potential collusion basically gets rewarded more. That's kind of the TLDR of it, and so. The second paper that I had cited there, they kind of replaced this model with a kind of mediator role where you would verify occasionally. And so, by the way, this first paper did not have. They assumed you're always sending 2 copies out of every job, which has kind of a high overhead. The second paper, they verified occasionally, but the verification happened with a kind of trusted node, basically a mediator. And the way it worked is that you would have a list of every client and every compute node would have a list of mediators that they both trust, and then if neither of them like the performance of the other, if the client doesn't or the compute node doesn't like the performance of their mediator, they can just remove them from their list of from their list of accepted mediators, and that's the kind of incentive for mediators, to be honest. And there's a few issues with that model, but that's the basic model. So. In that paper, they also were focusing on deterministic workloads in this scenario. I'll get to non-deterministic workloads in a minute. But in deterministic workloads, you can actually, of course, naturally, you can actually replicate the result, which is really important for actually double-checking the work. And in the second paper, I'll just skip to the end here. Mechanisms for outsourcing computation in a decentralized market. Basically, the way they did it was they had the mediator to check for non-determinism. They had the mediator repeat a computation n times to check if you get a different result at any point in time. And if you do, then the client gets slashed because this is a potential attack of the client. The client can, for example, send a deterministic workload or that they basically want, or even a non-deterministic workload, but then they can dispute the result from the compute node and therefore try to get the computation for free, which is kind of what they're trying to avoid. So they have the mediator run the computation many times in order to check if there's a non-deterministic output. And this is a bit of a bit of a security hole. I would say that probably the a safer method for doing this is basically to take those n repetitions of that same job and then to actually spread those n jobs across n different nodes, right? And so you actually have like almost like a Byzantine fault-tolerant kind of, in quotation marks, way for actually verifying the result of a computation. And so, and then, of course, you want to avoid malicious coalitions with high probability. And then, of course, you can allow any node to raise a dispute and continue to expand the set of nodes verifying, but this actually goes to global consensus, not local consensus. There it is. So per job pricing model. So how do we actually like price these compute? So this is kind of going to focus on a gas-based approach, like a gas in like the traditional blockchain sense. So assume that we can get deterministic results and we can count instructions. Ideally, we want to be able to count different types of instructions, like FP32, FP64, integer operations, and so on. That has a bit of an overhead, but this is kind of more idealized. And assume that we're paying per job, right? So you have some kind of like Docker container that you're running, and or WASM that you're ideally WASM, because that's how you get. You can be relatively sure about determinism in that case, and you're paying for the entirety of that job, right? You're not paying per time right now, and so you basically construct a two-sided marketplace for different components of compute. So you basically have a price. You can have like a price per FP32. FP32 instruction, a price per FP64 instruction. You could also have, you can go on and on. You can, of course, include memory usage in this, GPU compute, and of course, GPUs have FP32 and FP64, and now like int 8 or whatever, computations of their own. When the compute node returns a result, it returns its instruction counts. And usage of other resources. So it's basically this vector of numbers that it's returning about it's indicating its resource consumption. And then the client can choose to pay the pre-agreed upon price based on that result, or it can dispute, right? And if it disputes, disputing a price is basically actually the same as disputing a result. Right? Because how do you actually check that instruction count is correct? Well, you just send it to another node and you ask that node to compute the result itself, and then you basically just invoke the anti-cheating mechanisms that you were using before, right? So ideally, if that first node was honest when you send it to a second node, and if that second node is honest, it should return the same result with the same instruction count. And then the question is, how do we get to a per time pricing model, which is a bit more a bit more familiar in the traditional cloud computing sense. So again, assume that we can get deterministic results and count different types of instructions. And as before, compute nodes offer some cost per type of computational resource. However, now compute nodes also offer some amount of computational resource per time. Right, and so we basically have cost per resource, which is the parameter we had before, but now we have resource per time. Right, so I can offer you, and you could think about this like in a Docker container. You can set like the parameters of whatever that Docker container can hold, or the CPU limitations, RAM limitations, and so on. And so now that you have cost per resource times resource per time is cost per time, right? And that's basically like the kind of really basic general model of how you want to get to that. And then the question is, so how do you actually check for correctness or honesty from the compute node? And so you can, and then of course this isn't on here, but like naturally the way you would do it is you would have like an escrow from the client, like a pool that's used to pay the compute node. And as long as the job is not finished, then the money would move, or the payment would move. Parts of payment would move from that escrow either directly to the client or to some kind of intermediate smart contract that can maybe be disputed or revoked for safety purposes, and then that would pay out slowly over time for every single step of this operation. And so. But we still have to be able to check for correctness and honesty, and so there's a ton of questions around this. So, can we compare subsections of the computation? So we can compare subsections of the computation. So we could take a snapshot of the WASM memory and then, just check, let's say we split the computation into 100 pieces. We could check, checkpoint 57 to 58, right? And, see if you get the same result out. The problem is with the bandwidth consumption for this might be very, very high, right? So if you have like a 10 gigabyte job, which is not unrealistic, you now have to send a 10 gigabyte snapshot of the WASM memory to another node in order to check whether step 57 to step 58 was actually done correctly, and that can be like really, really expensive, right? And so the question is it possible to analyze subsets of the computation in a totally generalized way that gives the same guarantees as recomputing from scratch? So, can you, for example, take any subset of the computation and only check that and still have the same like runtime and or other like for example, if you have if you take you only need to compute like 1/5 of the original image, you want the runtime to be 1/5. Can you achieve that in a way that guarantees the same that has the same security guarantees as recomputing everything from scratch? And that's a question. There are people working on it. To the extent of my knowledge, that's not totally doable, but maybe we'll find a way to do it in the future. And then, of course, what about not as good guarantees? So, well, what if you don't have the same security guarantees, but you have some decent security guarantees? There's a trade-off in there, and that's kind of a theme in general in the game theory industry. In kind of verification and via replication, there's always trade-offs, right? The more you're willing to pay, the more security you're going to have. So then we get to deposit economics, and predicting the cost of a job in advance might be easy in some cases, but in general it's really difficult. There are some exceptions to this. For example, if you're running inference on some AI model, you have a rough approximation of like the number of operations required to do inference on a neural network and so on. But in general, it's really hard to predict. And so, this is kind of a challenge, and this is why even per job and per time pricing, has these kind of internal issues with them. And so, naturally, you want the deposit needs to be used as collateral for slashing, and the higher the deposit relative to the estimated amount the task will cost, the higher the security. This is coming also from that second paper I mentioned. The issue is that when you have a very, very high deposit, and actually, skip to the last point here, collateral has to account for potential cheating and not getting caught until a task is chosen for replication. So hypothetically, if you're only getting 2% of your tasks looked at, verified via replication, you could probably cheat for a while until you get caught, right? And so when you do in fact get caught, you want the deposit in there to be high enough to actually make having cheated on all those prior jobs, non-dominant strategy. And so, the problem with this, of course, is that there's a massive capital inefficiency caused by using very high deposits. If you're, for example, you could just imagine the number of jobs that a machine can actually do at a single time, and then you have to put down collateral for every single one of those jobs, that can actually become really, really expensive. Pooling resources like insurance might solve this problem, but in general, it's kind of an issue because it also costs a lot to join the network, and you could also potentially replace this with reputation as well, and I'll just get to that in a minute. So. Just kind of some miscellaneous points. Well, there we go, sorry. Some miscellaneous points. So there's a really interesting heuristic in that the decentralized computation marketplace paper, where basically, clients and compute nodes choose who their mediators, directories, and solvers are. And if two nodes do not agree on, or rather, if a single node doesn't like how their mediator performed, or in a solver here, by the way, is a market maker. I'll get to that in a second. If a node doesn't like how their mediator is performing, well, they could just remove that mediator from their list of trusted mediators. And it interestingly actually creates a market for mediators, and that's the kind of idea they have around how to actually get mediators to act honestly. And otherwise, mediators are basically just other compute nodes. There's really no other difference. So most clients don't really want to choose their compute nodes manually, or even define their own algorithms for doing so, right? So if you're thinking about how a client might use AWS or Azure or GCP, they are not choosing, they're not choosing a bunch from amongst a list of machines that all have different prices. I mean, there are different tiering options and so on, but within those tiers, that's totally homogeneous. Your options are totally homogeneous. Whereas in this environment, you're going to have a really, really heterogeneous set of hardware, heterogeneous heterogeneous set of prices, especially because you're going to have different local electricity prices. You're going to have different local bandwidth prices, and then even actually different local hardware prices, and so on and so forth. You're going to have this very heterogeneous set of prices, and who on earth wants to actually look at like this list and actually pick from them? And so there is a space for solvers, right, market makers, dispatchers, whatever you want to call them, that actually do the market matching between clients and compute nodes, and provide that bridge that makes that problem pretty easy. And so, of course, naturally, if assuming that those solvers and so on are behaving honestly, and that is another issue, arguably another issue with that paper, but assuming those solvers are behaving honestly, they basically have an incentive to do as efficient a matching as possible between the clients and the compute nodes, while simultaneously maximizing their revenue. And that might involve, especially when you consider all of the complexities that might involved in this market matching, that might involve like some very, very complex algorithms, and you could have like a genuine market for these and business models around designing algorithms in order to do that. Additionally, you could, if you're trying to do something like a global consensus, you could also have a smart contract do all of that, and that the design of that smart contract would have to be agreed upon by the network participants. There are issues with that as well. Just naturally, people will still try to game that. But at least there is one simple set of rules for everyone, and that's kind of fixed and kind of deterministic in that sense. In the literature, there's relatively limited analysis of repeated games and bounded rationality and real-life behavior, right? So all of these games are repeated games. If you go to a client, or rather, you have this marketplace of clients and compute nodes, a client is usually probably going to send out more than one task in their lifetime, and a compute node is going to compute more than one task in its lifetime. And so these are actually very much repeated games, that's a kind of a gap in the literature. And then, of course, we have bounded rationality, real-life behavior. Not everybody, as we know from behavioral economics or just common sense, not everybody is a utility maximizing rational agent. Arguably, does utility even exist? But whatever, that's a different story. I'm just kidding. But there's another question of are analytic solutions the way to go in these environments? You can try to define, for example, in that first paper, the smart contract, prisoners contract one, they found like it was really phenomenal paper. They found a way that their method basically induced a sequential equilibrium, which is like a very, very strong form of game theoretic equilibrium. It basically means that you have this tree of potential actions, and then along every single path in that tree, the most rational action leads to both nodes being honest, basically. And that's a very, very strong form of equilibrium. In the second paper, they found a Nash equilibrium, if I remember correctly. The question is, are these types of analytic solutions the way to go, right? Because, again, none of these are taking into account like real-life behavior, repeated games. They're all doing verification via replication, but in a truly robust marketplace, you would have T's and snarks and any type of general computation. And so every single time you add one more parameter to this set of possibilities, like the results start breaking down. The results will almost certainly, the analytics results will almost certainly start breaking down, right? Because the complexity of the problem just increases massively. Also, non-deterministic jobs can be supported by these models, and so there's a lot of focus on deterministic tasks because they're very easy to replicate. But if the compute node can't tell that is being sent a non-deterministic task, it can't really distinguish, between a non-deterministic task and a deterministic task. And so it's better off playing it safe and assuming that it's deterministic. If you start really introducing a probability that it might be non-deterministic, that again changes the game theory and so on. But most compute nodes are probably not going to do that. And of course, you do have to account for the ones that are, though. I think I have a point about that in the next slide. It's also really important to note that the game theory changes quite a bit when the client actually does have enough hardware or does have the computational power to check a result for themselves. If we're talking about, I was describing here basically the initial copy of the task is sent to one compute node and then the verification is done by another compute node. It doesn't actually have to be done that way. The reason most people use cloud computing and so on is because they don't have the local resources required to do all of the computation. Either their hardware isn't powerful enough to do it at all, or they don't have enough hardware to do all the computation they need, and that's why they outsource computation in the first place. But if the client does in fact have enough hardware to do the computation by themselves, this does change the game theory a bit. And you can get into that, for example, like you send out a task to a compute node, you want to check 1 out of every 100 tasks, or 1 out of every however many tasks, to check if it was actually done correctly. And if you dispute it, you still need to have if you dispute that, you say, oh, that compute node lied to me and didn't give me the right result, you still need to be able to check that, or not you, the client, but like the network needs to be able to check that you, the client, are being honest about them lying, right? And so that's a slightly different scenario, but it's kind of solved in a similar way, right? You just want to have like a subset of nodes all run the computation themselves and then compare the results. So basically a robust distributed computing platform would have the capacities for trusted execution environments, snarks, ZK snarks, eventually fully homomorphic encryption when we get to that, and so on. And the question is how to best balance the needs of the clients and the resources of the compute nodes. There's no, like I said before, are analytic solutions the way to go? I'm not sure they are. I think simulating this is probably the best approach that we can have, simply because, again, every single time you add another parameter to this kind of really complicated environment, it's too much for mere mortal mathematicians to try solving analytically. Maybe AI mathematicians in the future will be able to do a better job. I wouldn't be surprised, but we're not there yet. And so we do want to be able to account for example, you have to take into account like what is the benefit of using a snark or a ZK snark, and what's the overhead, what's the computational overhead. It's going to cost a lot more, but if you need the privacy or so on, if you need to know that it was done correctly, well, that's a different story. And then the same thing is true of trusted execution environments. So T's, for example, what's the overhead of setting it up? What's the overhead of running inside a T, which I understand is very, very low, but still should be taking into account the cost of doing that versus doing it natively. It's also important to note that stream processing is, the stream processing scenario is different, right? So nodes might not be available for the entirety of a job cycle. The value of the output decreases with time and so on. And so there is a slightly different game theory in this environment. And the authors of the decentralized compute marketplace, they followed up with a really good paper on a streaming compute marketplace as well. And I would recommend people read that if they're interested. Then there's this issue of reputation, and reputation is a really, really big kind of pink elephant in the room, because why can't you use reputation for these nodes? And there were all sorts of these kinds of algorithms in the 2000s, like eigentrust and power trust and peer trust and so on, that were designing reputation systems for nodes. For distributed either like file storage or distributed computing and so on and so forth. And the question is, why can't you use this? And the answer is it's not that you can't. In fact, a robust distributed computing platform would have capacity for reputation, right? You really want to have the capacity for any one of these kind of models, but the reputation gets tricky, but it also could be very useful. So, for example, you could just be willing to pay you might be willing to pay more for nodes with higher reputation. But you also have to be very, very careful, because nodes can build up a very, very good reputation over time, and then if they're checked very infrequently, they can start messing things up if they want to, and that's what a malicious node would do, but not necessarily a utility maximizing one. And the kind of space of what can be done with reputation is like really, really large. And so there's also other questions, like, so what happens if a client goes to a compute node as a repeat customer versus using just uniformly choosing amongst the nodes that have their bids within some range? Does this change the game theory at all? And naturally, if all clients are using the same verification strategy, then an expectation honesty will still be a dominant strategy, right? But if the clients have different verification strategies, that might not be the case, right? So if one client only verifies 1% of the time, but another client verifies 10% of the time, well, if a node is able to, if a compute node, malicious or rather utility maximizing compute node is able to kind of observe, how often each of these nodes replicate and kind of switch between the two, and notice how often it happens, that kind of changes the game theory quite a bit as well. And these are, this amongst that plus the repeated games and so on and so forth. This is why I kind of advocate more for the simulation strategy rather than kind of going for analytic solutions. And a couple of other things that we kind of would want to know about are we do need like a list of potential client attacks. So like one of the most obvious client attacks is to get a task computed for free and not be called out on it. And obviously the client needs to put up stake and so on and so collateral to make sure that doesn't happen and so on. But the question is, what other attacks can clients launch, right? Other than like software, viruses and so on. Like, what other kind of potential manipulations can clients do? And then another question is, can we get determinism on GPUs? The answer is, from what I understand, basically yes, but it's a bit complicated. I know that there are people working on getting determinism on GPUs, getting determinism on inference, both on inference and on training. It's a bit tough, but my understanding from what people I've spoken to is that it is very much possible. These are those two papers that I cited. There's plenty more, but these are kind of for people who are interested. I would say that these are the kind of like two kind of critical papers if you're interested in learning more about this. And yeah, I think that's everything. And yeah, thank you. And I'll take any questions if you'd like. Thank you. Yeah. Yes.
Can you go back to the slide with the diagram?
There's a slide with a diagram.
That was a trick question.
Oh, okay. I was you convinced me for a second. I was like, wait a minute. There was no diagram in there. Okay. That was good. That was really good. Any questions? Any serious questions? Yes.
Yeah, I have two. On the deposit economics, does this put like a bound on the price of a job?
Okay, so the question I'll repeat it. So do the deposit economics put the bound on is it the cost of a job or what was it?
Because, I don't know, my intuition was that if you can have some very expensive jobs, or arbitrarily expensive jobs, then the deposit economics that you talked about might not work.
Yeah. So that's a bit of an issue. So if you have, so the question is like, what happens if you have like a really, really expensive job? And the authors in this last paper here, the very last one, they basically said you just have to put in like a lot of slack for the potential cost of this job. Oh, actually, the slack is actually more for also for being able to pay for the mediator rerunning the computation n times. But yeah, that is an issue, right? And I think I said this. Predicting the cost of a job in advance might be easy in some cases, but in general, it's very, very difficult, especially if you have a non-deterministic workload, or if you could just hit some if-else statement, and then suddenly your computation is taking like 10 times longer than you thought it would. Oh yeah, additional collateral must account for potential cheating and not getting caught until a task is chosen for replication. Well, that's kind of another issue insofar as. Like if you're only verifying 2% of the jobs, you can get away with cheating for a really, really long time until you get caught. Especially if you're really playing some like complicated game where you're only like cheating for like 10% of the jobs here and there, and then you're just waiting for who knows, like people will go to great extents to break things even for fun, let alone for money. In terms of like paying for the unpredictability of the cost of a job is a really, really challenging problem in this environment. Arguably the ability to break up a job in that kind of per time pricing model that I described, that could that method where a client can say, hold on a second, is this job really, should this really cost this much? You know, is this being computed honestly or correctly? I don't know why that went out. But you know, is this being computed honestly or correctly? You know, it's actually, to the extent of my knowledge, that I haven't seen people address that in the literature. I thought about it myself, and my basic answer is you just have to have enough in there to pay for anything like that. And if suddenly, for example, if you're in the per time pricing model where you're just paying incrementally, as long as the compute node says that the job isn't finished, well, what you would basically have to do is, if the money in your escrow is out and the compute node's saying this job isn't over, well, first of all, you might want to just check if they're cheating, and you might want to rerun a small subset of the computation. But otherwise, you have to put more money in your escrow, right? They can just, if it's a WASM, if it's running WASM, they just freeze the memory state and just wait until you pay more money. It's not a great solution, but there might be, and hopefully will be, better kind of models for that computation going forward. Yeah, and yeah, any other questions? Did you have a second one, or a serious question? Yes. Yeah, so streaming, yeah, so this mechanisms for outsourcing computation via decentralized market, the authors followed this up with a decentralized market for stream processing as well. And that is it's a different environment. So I should probably have prefaced this by saying that this is focused on what I'm describing is focused on batch processing. The game theory is somewhat different for stream processing. But that wasn't covered in this talk, but there is a robust thing. We can definitely talk about it after. And yeah.
Yeah, and there's the stream processing paper as well.
The paper. They followed up this. Oh, it's not there. This paper. The same authors, or a slightly expanded set of authors, followed this paper up with a paper in 2022, actually, focused specifically on the streaming market, decentralized streaming market use case. And did you have it? Yes.
So my other question was, why do you need to count different instruction types? Is it because they are differently complex?
So the question is, why do you have to count different types of instructions? And the reason is that different types of instructions, because different hardware have different advantages and disadvantages on different types of computations. And there's it becomes very, very complex because you really have to take into account the kind of diversity of motherboard, especially in a decentralized, kind of distributed system where people have gaming rigs and phones and tablets and so on and so forth. You have to be able to take into account, this combination of different motherboards and RAMs and CPUs and GPUs and BIOS settings and whatever operating systems. And the list goes on and on. The complexity, the things that cause complexities go on and on. And different machines are going to have different capacities. And they're going to be better or worse at different types of computations. And so they might all prefer to have a different type of price. To break down when they're charging somebody, and that actually helps both the client and the compute node because it helps match more tasks that are better suited for different types of hardware.
There's some CPUs that have specialized instructions for like
Yeah, exactly. So CPUs have specialized instructions for different subsets and so on. So yeah, that's basically the logic behind it. But as far as I can tell, based on people that I've talked to, where is it? The ability to count different types of instructions. In both of these models, that apparently incurs a pretty, like in WASM, apparently it doesn't exist right now, but it's apparently possible. But there's a very, very high overhead for counting different types of instructions, and that's a bit of an issue, right? So my understanding is counting instructions in general that can be done without much overhead, but counting different types of instructions, that's very expensive. But this was kind of a more idealized model. This is kind of how I was bringing that up. Okay, any other questions? All right, yeah, thank you again. Thank you so much for coming. Thank you.